So, carbon, as I said, is the star of the show when it comes to organic chemistry. Any molecule that has carbon as its backbone is considered organic, and it is the backbone that tells us a lot about what an organic molecule is. So, carbon, as you hopefully are aware, can form a maximum of 4 bonds. When it has all 4 bonds, it is very happy and it's very stable, which is why it's a good molecule to have as the base of organic chemistry. Okay, so let's start having a look at what happens with the different types of molecules that we get in organic chemistry and go through each type. Now, each type is called a homologous series, which means that from one molecule to the next within that series, they differ only by the number of carbons in the backbone. Okay, and I'll show you what I mean. For example, I've drawn out some molecules here. These are the hydrocarbons. These are the 3 hydrocarbon series that you need to worry about for Matric. Okay. Alkanes are saturated, which means that the carbons that are in the backbone are all very happy, they all have 4 bonds, and they are not very reactive. You'll see that alkanes are forming single bonds, 1 carbon to the next, and it's in the name. The suffix when you're naming an alkane is ane. Then you have the alkenes. Now, alkenes look very simple, but they have a double bond somewhere in that backbone. They can have double bonds in 2 places and sometimes even in 3 places, but anything where there's a double bond in the backbone is an alkene. Okay, alkenes are a little bit more reactive than their alkane siblings, but they have a different set of properties, so they are different homologous series. And then lastly, you have the very biggest brother, the alkynes. They have a triple bond somewhere in the backbone. Now, the reactivity doesn't actually differ very much between them, and in fact, alkynes are maybe even slightly less reactive sometimes. Yes, I haven't been teaching this course, just looking at the chat. I haven't been teaching in this lecture series yet. Okay. So that's the hydrocarbon set. Then we can have a look. Hello. Why is my, there we go. At the carbonyl groups. Okay. Carbonyl groups are any carbon that has a double bond to an oxygen, but we divide this up even further. We divide it up into aldehydes, ketones, carboxylic acids, and esters. Aldehydes, they have a terminal carbonyl group, so a carbon on the end that's hanging on with a double bond to an oxygen. That is also sometimes called is also sometimes called a 4-mil group. But you'll always be able to tell these apart because they have the YDE suffix. Then ketones. Ketones have somewhere in the middle of their backbone, they have that double bond to an oxygen. A lot of the important molecules that are in your body, for example, glucose in sugar, have ketone groups. Then you have the carboxylic acids. They have a terminal carbonyl group, but then they have the hydroxyl group as well, which is an OH group. All right. And these are always denoted something something oic acid. And then lastly in this family, we have the esters. Esters are a bit of an oddball because they're made up of a carboxylic acid and an alcohol. So when we are looking to identify an ester, what you are looking for is the bond complex that's highlighted in red in this column. This double bond to an oxygen, and then an oxygen bridge to another carbon backbone. Is that clear to everyone what the difference is between an ester and a ketone, for example? You can put thumbs up in the chat, or you can, yeah, okay, wonderful. If you need me to repeat something, just say, okay. So, esters, you have that oxygen bridge to another carbon backbone. And when we name them, now this is where the slightly trickier part of naming for these comes in, is that they sort of take a double barrel name. They will be, for example, methyl methanoate, depending on which backbone had the carboxyl group and which backbone had the alcohol group. We always look, when we're naming an ester, first at the carboxylic group and then at the alcohol group. Sorry, I completely blanked on that name. So always first at the carboxylic group and then at the alcohol group. All right. So the last thing we need to talk about are substituted hydrocarbons. So these look exactly like a hydrocarbon, except somewhere on these we have an atom set that is not hydrogen and it's not carbon. And I was just talking about them. The alcohols are one type. So they have an OH, which is called a hydroxyl group, and they have only that. So it's not like a carboxylic acid where they have this and then the double bond oxygen. They just have the OH. And it is usually, but not always, on the end. Okay? And these are denoted methanol, ethanol, propanol. And you can put a number in between the AN and the OL to denote where on the backbone the hydroxyl group occurs. Okay. Then very lastly, we have the haloalkanes. So what happens on a haloalkane is that rather than have all hydrogens around one of your carbons, you substitute one of those hydrogens for fluorine, chlorine, bromine, or iodine. These are often intermediaries in processes. They don't normally hang around, but you should know how to name them. And to do this, you add, this is the only one that you do where you add a prefix rather than a suffix. So these are fluoro, chloro, bromo, or iodo, and then the rest of the name. I didn't write this down on my slides, but it's always good to remember the names for the backbone lengths. So firstly, your very simplest ones with just one carbon, they are methanol, M-E-T-H, or methane. Well, methane doesn't exist. Methanol, methane. Then you have F-E-T-H, ethanol, ethene exists, and then prop, P-R-O-P, is for 3 carbons, and for 4 carbons, you use but, B-U-T. After that, they take the same names as, for example, shapes that you learned when you were in primary school. So pent for 5, hex for 6, hept for 7, and so on. And you need to know up to 9, which is non, N-O-N. Okay. So, with all of that in mind, what is the IUPAC name of compound B? You guys can put answers in the chat, but I'm going to show you how to approach this and how to work through it. All right. Am I seeing I will check the chat as answers come in and maybe try, if they're incorrect, to work through the misconception. But let's get started. So, when you are naming an organic compound, you are always looking, first and foremost, for the longest continuous chain of carbon-to-carbon bonds that you can find. So, in this molecule, the longest carbon-to-carbon chain starts at the top and ends on the bottom right. Okay? Not necessarily in that direction. We'll count out which direction it goes in a second. But it is this long central carbon chain. These two carbons on the side are side chains. Okay. So they do not contribute to that number name. So meth, eth, prop, but, pent. They are not going to contribute to that. All right. So these are methyl side chains. Okay. Now, if we have a look at what functional groups we have here, the only functional group are these two bromines. Okay, so this is a haloalkane. You can see there are no double bonds between the carbons, so we're dealing with some kind of alkane. Okay. Next up, I did mention the two methyl groups. Okay, and they are behaving as side chains. So again, they're not going to contribute to the number name of this alkane. Okay. Now, with that information, we have two bromines and two methyl groups on a 6-carbon chain. Can anyone please put in the chat what would, if there were no like extra functional groups attached to it, if I just had 6 carbons in a straight line with all single bonds, what would the name of that be? So would it be methane? Would it be ethane? Would it be butane? Would it be octane? What would it be? Hexane, yes. Okay, wonderful. Yes, this is a hexane. Okay, so this is a hexane, and you can see that it is substituted. Okay, now we need to decide on a direction for this hexane. So, when you are deciding a direction for an organic compound, you are always looking for the direction that is going to bring you to the functional group first. So, to the functional group as quickly as possible, you could say. So, if I was to count this from the top, remember that our functional groups are the bromines that I've highlighted in green here. If I was to count this from the top, bromines would be on carbon 4. But if I was to count it from the right, the bromines would be on carbon 3. So that's the direction that we're going to count. We're going to count from the right, which means that we have a dibromo on carbon 3, so 3,3-dibromo. And then on carbon 4, we have two methyl groups, so 4,4-dimethyl hexane. Okay, is everyone clear on how we got there? Okay. Okay, I'm seeing a no in the chat, so I'll go through it again. Okay, I'll give another couple seconds for people to say yes or no. Okay. Okay, getting lots of yeses. Okay, getting another no. Okay. Okay. So now there's suddenly no's coming in. All right, that's fine. So let's go back. Where did I lose you guys? Okay. So, can someone just tell me where I lost you so that I know where to go back to? Okay. At what step of the process are you getting lost? So I can go back there and maybe clear up any misconceptions. Okay, where do we start from if we have a branch? Okay. When you have branching on any compound, you are always looking for the longest continuous chain. In this situation, if you were counting from like the ends of the branches, you would be counting only 4 carbons. Because remember, a carbon chain, you can't go up and back down a branch. So you have to keep going continuously. You can't like turn around and come back. You can't make a U-turn when you're counting carbons. All right. So when you have branching, you look for a long continuous chain of carbon. All right. If that means you start counting from every direction and see how many carbons you can catch, if you want to call it that way, in that direction, then do that. Why can't you say it's pentane for the longest chain? Because if you... Which way are you counting for pentane? Okay, I can see which way you're counting. So you're counting from the right and you're going to the bottom. All right? Okay. So, because pentane would not be the longest continuous chain, because it would be longer if you went from the right and then you turned and you went to the top. Because that way you have 6 in a row. So you're always looking for the highest possible number of carbons in a row. So I can see why you would think it might be pentane, but it's with just checking. Okay. Count from the right in this case, so you're on the right track, but then you have more carbons on the top branch than the bottom branch, so then you're going to go up the top branch. Does that make sense? Great. Okay. Then, when you are naming this, okay, where we're going through. So then when you're naming, now that you've established that your longest hydrocarbon chain is this 6 that I've highlighted in this yellowy orange color in the middle, then everything else has to be a side chain. It has to be. It's like if this is the highway, everything else is a side road. That's kind of a way you can think of it, right? So we found the highway. The highway is the yellow stars. So everything else, it can have carbon in it, sure, but everything else is a side road. All right, everything else is a side chain. So these 2 methyl chains that are hanging on the side here are side chains that I've highlighted in blue. All right. Please. Okay. Okay, if you missed something because of network problems, I understand these lectures will be uploaded to the Learning Space social media. So you can go back and watch, but I'll quickly recap how to get the longest chain. In this case, I'm counting from the right-hand side of the screen and going to the top branch rather than the bottom branch, because on the top branch there are 2 carbons and on the bottom branch there's only 1. Okay, why should we start counting from the right-hand side? All right, that's a good question. And I can tell you that there are first-year varsity students who don't know why we should count from the right-hand side either. So, why you should count from the right-hand side is when you are looking for which direction to count, all right, you're always looking for, if we use the road analogy, you're looking for the road of carbon that's going to bring you to a functional group the fastest, okay? So it's like when Google Maps shows you the fastest road. You want to get to the functional group as quickly as possible when you're counting. So in this example, now that we've identified our backbone, so you're not supposed to start from right to left. In this molecule, you are, but not all molecules you count right to left. There will be one later on where you're going to count from left to right. So it really just depends on what's going on in that specific molecule, okay? Because when you are counting this, you want to get to your functional group as quickly as possible. So if we were counting from the top, there are 4 carbons before we get to the bromines. If we're counting from the right-hand side, then you're going to have only 3 carbons before you get to the bromine. Okay, and that's how you decide which way to count. So it's not always necessarily going to be bromine, but it's going to be whatever functional group you find first. So in a pure hydrocarbon where there are no functional groups, it doesn't matter which side you count from. But most organic molecules have functional groups, so then you need to get to the functional group with the lowest possible number. Yes, you're prioritizing the halogen. A halogen takes priority over a carbon side chain. Okay, Kefilwe, I think. If I'm pronouncing your name wrong, I'm very sorry. So yes, in this case, your halogen is taking priority over your carbon side chains. Okay. Halogens will always take priority over carbon side chains. Is it wrong to start counting from the carbons in the branch? Yes. You cannot ever start counting from the branches. You have to start on one end or the other end, okay? It's like if I told you that the N1 goes from Uppington to Johannesburg. It doesn't. It goes from Cape Town. The road to Uppington is a side road. Okay. So you have to start at one end and at the other end, or at the other end. Okay, you cannot count from a branch. That's a fundamental rule of how IUPAC nomenclature works. All right. Are there any more questions about how we got to this name? The 3,3-dibromo 4,4-dimethylhexane. Okay, no, from left to right or right to left is not the same in this molecule. There is a difference. And the reason that we order the bromine before the methyl groups in the name is because you put the prefixes in alphabetical order. Yeah. Please start all over. Okay. Why is there only one halogen on carbon number? If there was only one halogen on carbon number 3, that would still be the functional group in this molecule. So you would still start with the halogen. It would just be 3-bromo 4,4-dimethylhexane. Okay. I'm gonna go back to the top, do this molecule just one more time. All right? Just go over how to name it. Because this is quite a meaty molecule. There's quite a lot going on. All right. Okay, let me just go back. Okay. So, very first thing we're going to do is we're going to identify what our longest chain is. The longest chain, you are always looking for a continuous chain. You're not counting any branches on the sides. You're not going up a branch and turning around and coming back down. The longest continuous line of carbon, 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 carbon that you can find. Okay. So in this case, that longest continuous line of carbon, 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 carbon is this axis right-angled thing going down the middle and to the right. Okay. We also identified the functional group, which are the bromines in this case. And then we look for any side chains, which we've identified these 2 methyl groups as side chains. And that is our longest carbon. longest continuous chain of carbon, so the backbone. Okay. Then from uh um from here, we need to decide on a counting direction. All right. So to count this, let me just find a pen. Okay. Okay, to count this, if we went that way, all right. Sorry, I'm drawing with a touchpad, so it's a bit difficult to get nice drawings. If we went that way, down this carbon, we would end up getting the bromines on carbon 4. Now, that's theoretically okay, but let's see if we can get the bromines on a lower number any other way. So what if we go this way? Okay. Going that way, the bromines are now on carbon number 3, which is what we want. We want the functional group to be on the lowest possible carbon number. We want to get to the functional group as quickly as possible. Okay. Yes, okay. Uh, is the gnawing and knowing in the chat for me, or is it for someone else? Sorry. Okay. Then, from here, now that we've put the bromines on carbon 3, on carbon 4, you can see we have the 2 methyl groups. And from that, now that we've identified both sets of substitutions, we can give it the name 3,3-dibromo, dibromo because there are 2 of them, okay, and they're both on carbon 3. And 4,4-dimethyl, again, there's 2 of them, they're both on carbon 4, hexane, because this is a carbon chain that only has single bonds, and there are 6 carbons in that chain, hence hexane. There we go. And I've color-coded the names that you can see where each part of the name is coming from. Is this a bit clearer for everyone? Okay. Okay, I'm glad. Good. Okay. Please explain the part in the bracket when they have given you the name. Do you mean molecules like E, F, and H? We'll get to those. Okay, we'll get to. Okay, yeah, that's a good way of donating it. This is the way you can say that you are counting from the carbons that are closest to the highest priority, that you can count from that. Yeah, so the carbons closest to the highest priority group is where you would count from. Yeah, that is correct. But I was just using an analogy, but you are correct. Okay. Where did we get 4,4-dimethyl? The 4,4-dimethyl, if you look where my blue stars are, there are each of those blue stars is a methyl group. So yes, I'm going to move on in a second, but I want to make sure everyone understands before I move on, okay? The 4,4-dimethyl is because on carbon 4 there are 2 methyl groups that are hidden under the blue stars at the moment. Okay, great. Let's move on then. And oh my word, I have now annotated and not erased. Okay. What is the name of compound E? And I did say I would get to how to name and draw with these units that are in brackets. Okay, so I have drawn out this molecule for you, but what I would suggest is I will give 2 minutes for everyone to first try drawing this molecule for themselves. Unfortunately, you can't upload your answers or anything, but please try and draw this molecule, and then I will walk through the process of how to draw it, and you can check yourself as I do. Okay. 2 minutes, see if you can draw it. Okay, I'm seeing some dones in the chat. So if you're not done, that's not an issue. We're gonna walk through how to do this now all together. Okay, so let me start by showing you what this molecule looks like. Okay, so this molecule is an alkyne. All right, but we'll get to what it is and why it is in a second. All right. So for compound E, the first thing that I've gone and done is I always start by separating out each carbon by itself with its substituted groups, okay? So this is one group here, that's CH3. This is one carbon with two methyl side chain. Okay, that's how you read this in organic chem. Any CH unit in brackets is a side chain. All right, so that's what brackets mean in OChem. They mean that whatever is inside those brackets is a side chain of some kind, especially if it's carbons in that bracket, then they are carbon side chains. All right. Don't understand my structure. Can I explain how I got there, and then maybe we can discuss once I'm done, okay? Then there are two more carbons that have nothing substituted on them. Okay, they're not attached to anything else. And then there's this CH3 on the end. Okay, so let me show you how I got from breaking it down like this to drawing it out the way I have. Okay, so that CH3, I just put it right down. Okay, then the next carbon, I'm gonna have to draw out all of its bonds so we can put that carbon down, and then this has two substituted methyl groups. Okay. How do I know that these are not carbons that are, for example, further along in a chain somewhere here? Okay. How do I know? That was a very ugly arrow. How do I know that these carbons don't go in here? Okay. These are CH3s. If you're seeing CH3, anywhere in a molecule, except on the very, very ends, okay, you know it has to be a side chain. Why? Because carbon can only make 4 bonds. If I had CH3s in the middle here, that would mean that these carbons would have to be making 5 bonds, and that's not possible. Okay. So that's what tells me, that fact that they are CH3 is what tells me that they have to be side chains. Okay. Is that clear to everyone, how I made that decision? Okay. Um, Maybe is my network a bit slow? Can I just ask the admins to let me know if my network's a bit too slow? Okay, network's good. Thank you. Okay. Yeah, sorry, if the network is glitching on your side, it might be worthwhile checking your router because the admins are saying that there's no glitching on their side and we're on completely different networks. Okay. So, this is how I put down my 2 side chains. Okay. Now that we've got the side chains down, we can move on to this next carbon. Now, what's interesting about this carbon is, can you see that these have nothing attached to them except each other? And I told you that carbon has to, for it to be happy, has to make 4 bonds. So for example, if we took these 2 carbons and we just put them like this, with nothing else attached to them, they wouldn't be satisfied because now they only have, okay, they would be like this, 2 bonds each. And carbon is not satisfied with having bonds. Carbon wants to have 4 bonds. So to satisfy themselves, these 2 carbons are going to form a triple bond, and that's where this triple bond comes from. This triple bond, I saw there was the question in the chat, what is the functional group? This triple bond is the functional group in this molecule. This is a hydrocarbon, which means it doesn't have any, call them unique atoms. Okay, it only has carbons and hydrogens. So the functional group here, the group that's going to react, are these carbons with the triple bond. Okay. So that's that. Okay, and I will come back to that as well. Okay, please repeat. Okay, so how did I get a triple bond in this molecule? How did that happen? Let me draw it. Okay, let me pick a different color just to make it a bit easier to see maybe. Okay, if I took these 2 carbons up here and I put them into my molecule, so say I had already drawn this portion there, and I was moving on to put in this carbon. Okay. Oh, no, please don't do that. Okay. Say I was doing this, and I said, okay, well, I've got this carbon, happy days, and I'm gonna go here, I'm gonna put a carbon. Oh, and there's another carbon, so I'm gonna put another carbon, and there's the CH3. Whee! And done. Okay. That would be incorrect, because now each of these carbons that I have here is only forming 2 bonds. Okay, I hope that's clear. 1, 2. This carbon, 1, 2. That's not going to do. Okay? Carbon wants to make 4 bonds. And if there's nothing on the side available for it to make 4 bonds with, and there is nothing, it tells you there's nothing next to it, so it can't make those 4 bonds with something off to the side of it like this one's doing. It has to just double or triple bond to the carbon next to it. So here, that's why, to make it 4 bonds each, they're gonna make a triple bond. Okay, and that's how I got to this triple bond in the middle here. Okay, and that triple bond is also what makes this molecule an alkyne. It's the functional group, it denotes the homologous series. This molecule is an alkyne, YNE. Okay. 4,4-dimethyl pent-2-ine. That sounds good. Okay. So let's move on to talk further about this molecule. I'm not leaving this molecule behind. Okay, so this is how I got these 3 carbons to be happy. Great. So now, I've highlighted again the side chains in blue. Okay, these guys are very clearly side chains because if I was counting this way, so say this way, I would only have 3 carbons. 1, 2, 3 carbons. If I was counting this way, I would have 1, 2, 3 carbons. If I was counting this way, I would have 1, 2, 3, 4, 5 carbons. And that's fine. This does work. Okay? But let's just stick to counting down the axis. Okay? Straight line. Okay. This way. So here's 1, 2, 3, 4, and 5. Okay, I didn't put numbers on 1 and 5 because they are not doing anything interesting. They're not giving us a functional group. They're not... how would this look like if it had a double bond? Okay, we can get back to putting a double bond in this molecule instead of a triple bond after I'm finished naming this one. Okay, I will come back to that because it is a good question. Cool. So, 1, 2, 3, 4, and 5. Now, this molecule has 2 methyl groups again, so it is a 4, because it's on 4, 4 dimethyl. Now we need to figure out what the chain name is. It's 1, 2, 3, 4, 5, so that's pent. 4,4-dimethyl pent, and we know it's an alkyne, but we need to specify where in the molecule the triple bond is. Okay, so in this molecule, it's between carbons 2 and 3. So we say that it is starting, if you think about everything growing from this direction to this side, so everything is growing this way, this bond starts at carbon 2. So that is how we name it. We name it like this. Is it going? No, it's not. Okay, we name it 4,4-dimethyl pent-2-ine. Okay. We specify where in the molecule this triple bond that we're looking at is. It's between carbons 2 and 3. All right. Before I go back and show you what this molecule would look like if it was a alkene instead of an alkyne, is everyone happy with how we got to this name? Okay. Yeah. Okay, lots and lots of yeses. All right. So let me show you what this molecule would look like and how it would be written if it was, for example, an alkene. All right, so let's do the alkene situation in green. This green rhymes with alkene. Okay, so you would still have the terminal carbon CH3 that would stay. You could still have a carbon with 2 methyl groups that could stay. But what would happen here in this little bit? Sorry, the drawing is very messy. Okay, what would happen here? All right, so if you had a double bond, this molecule would look exactly the same. So you would have, oh my word, that's very small. CH3, you would have your carbon with your methyl groups on either side. I'm sorry if my handwriting is really bad. I'm doing my best. Please bear with me. Your methyl groups on either side. And then you would have a carbon double bonded to a carbon with a single bond going to the terminal carbon. Okay. Now, for this to be possible, there would have to be necessarily something else for these carbons to bind to besides each other, which there isn't in this molecule. Okay? Molecule E does not give these carbons anything else to bind to but each other. So for this to work, we would have to have hydrogens attached. Okay. Because then each of these is making 4 bonds. Then each of these carbons is happy. But this cannot come out of, oopsie, the notation for molecule E that we were given. Because we don't have CH. They would need to tell us that each of these C's has an H attached to it. Okay. This cannot happen from the molecule E. Okay. From the molecule E, the only solution is to make it an alkyne. I cannot remember who asked the question, but can you please put in the chat if that answered what you were thinking and if that cleared up a misconception? Just a yes or no is fine. What about a halide? Okay, then the name would change. Yeah, you could attach it to a halide, but I'm working with the simplest case. Yes, it could be a halide instead of a hydrogen, but they would have to be something else. Okay. The name of that molecule would then be very similar. It would still be 4,4-dimethyl, but rather than being pent to it would just be pent to ene. So all of this would stay the same. So I'm just going to put little quotations. But this would turn into being pent to ene. Hope you can see that. It's very small. Okay. That's all that would change. But if you had a halogen, that would change the naming completely, and I'm not going to scratch in that. But go and do that for yourself as an exercise. Take this molecule, do some reactions on it, add some halogens to it, and see what happens. Okay. It's a good exercise if you're feeling pretty comfortable with this name and you're feeling pretty good with naming in general. It's a very good exercise to take a molecule that exists like this, change it up a little bit, and see if you can still name it. Okay. Yes. Yes, Nathan, you're right. The two has to be between pent and ein. Oh, I'm so sorry. I didn't realize that there are questions in the Q&A as well. I'm so sorry. Will I cover organic reactions? Yes, I will. Is the prefix for aldehydes not Al? Aldehydes don't get a prefix. Aldehydes, aldehydes get the suffix "ide." Okay. Attendee that said they didn't receive the data. I'm not entirely sure what you mean. If you are asking about what the paper is, this is last year's final exam. But I have typed out all the questions, so you don't need the paper to follow along with the lesson. Yeah, I'm not sure what you mean. And then would you be penalized if you wrote 4,4-dimethyl 2-pentyne? No, you wouldn't. That is an accepted nomenclature. It is slightly outdated, so it is preferred to write pent 2-ine, but it is not wrong to write 2-pentyne. Okay. In an older textbook, you might see it written this way, but the current preference is to say pent 2 ein. All right. I think that's answered all of the questions that are in the Q&A. Okay. Great. Then we're going to move on to reactions. Now, the reactions are the hardest part of organic chemistry, but they are absolutely essential. You have to know how to do the different reactions, and maybe fortunately for you, if you're someone who likes to memorize things, this is a lot of memorizing. All right. It's a way to get not a lot, but quite a few easy marks if you just memorize what all of the reaction conditions and products and reagents are. And I'm going to walk you through how they ask this, and I'm going to walk you through how to approach a question on a reaction as well. Okay. So, the way this is asked, and the way it has been asked for years now, is that they give you a reaction scheme, but they give it to you with blanks. If you don't know what a reaction scheme is, don't worry, I'm going to show you. Okay? A reaction scheme, in this case, I've color-coded mine to make it easier to see what's going on. But a reaction scheme is like a little map that shows you if I start here and I do this, I will get here. And if I start here and I do this, I will get worse. Okay, there are 3 types of organic reactions. Okay, and you have to know the definition of each one. So, a substitution is any reaction that does not change the saturation of that compound. Okay, what do I mean by saturation? A saturated compound means you only have single bonds between your carbons. Okay, that is a saturated hydrocarbon, okay, with all of them having hydrogens on. Okay, they all have their hydrogens on. Okay. If you're doing a substitution reaction, you are not changing the fact that these all have single bonds between themselves and that they all have something else to hang on to. So these don't necessarily have to be hydrogens. They can be a halide, for example. You can have a halide here. You could maybe have a hydroxyl group here. Sorry, OH, not CH. You can maybe have a hydroxyl group here. You can do lots and lots of different things, but at the end of the day, everything is a single bond between the carbons. Okay? A substitution reaction will not change whether there are single bonds or double bonds between the carbons. Okay. Then, a addition reaction will change that. Addition reactions are going from something that is unsaturated, oh goodness me, something that is unsaturated, sorry about my horrible handwriting, to something that is saturated. Okay? And an elimination reaction is going from something that is saturated to something that is unsaturated. I hope so far I haven't been saying anything new. You should all know this. I see I've been sent a message that my network is glitching. Can I explain the substitution one? Yes, I can. So, in a substitution reaction, for example, if I had single bonds between my carbons and I did a substitution reaction, I would still, in my product, have single bonds between my carbons. Okay? If I had double bonds between my carbons, I would still have double bonds afterwards. So it's not changing the number of bonds between my carbons. Is that helpful? Cool. No, please repeat. Okay, so if in a substitution reaction, let's use the molecule ethene as an example. Let's use ethene. C, double bond C, and I'm going to use this form of ethene. Bear with me, this takes a while. Okay. Ethene. That's ethene. If I did a substitution reaction on ethene, I could substitute. To substitute, have any of you ever had a substitute teacher? Your lessons don't get cancelled, and you don't get extra lessons added. There's just someone else taking that lesson. Same thing. That bond doesn't go missing. It doesn't move to be between carbons. It doesn't move out from being between carbons. That bond stays exactly where it is. It's just going to something else. So let's use chloroethene as the product. If I went C double bond C, and I had a chlorine here rather than a hydrogen. Sorry if that looks like a weird A, it's a Cl. Okay. Can you see that in this reaction, I had a double bond between my carbons when I started? I had some stuff. Something has changed. Oopsie daisy. This molecule looks different. It is something else. There's a chlorine there that wasn't there before. It has changed. Something has happened. But I still have a double bond between my carbons. Is that clear? Okay, good. So then let me erase this and let me show you what a reaction scheme looks like. Okay, if any of you go on and you go to university and you're studying chemistry or you're studying biology, you will see reaction schemes coming out of your ears. There's lots and lots and lots of them, so it's a good thing to get used to. Okay. Oopsie daisy. Just erase this as well, because otherwise it's all gonna muddle up my notes. Okay, here we go. Here is a reaction scheme. So let's start from the middle, because please don't get overwhelmed. I know it looks overwhelming, but I'm going to show you how to read one of these. All right. Starting from the middle with an alkene. This can be any alkene. This can be ethene. This could be propene, butene, pentene, hexene, any alkene. You're normally going to see alkenes. For your purposes, you're not really going to see the alkynes very much. So, but they behave the same. Okay, alkenes and alkynes behave very similarly for the purposes of a reaction scheme. All right. So from an alkene, let's follow this yellow arrow going up. You can go from an alkene to an alcohol by performing what's called a hydration reaction. And remember that we said that the yellow arrows, or the orangey arrows, I honestly don't know what color this is, yellow or orange, call it whatever you like. These yellowy orangey arrows are addition reactions. So we're going, okay, maybe let's add this to this. Let's do this. Okay, alkenes are saturated. Okay, so now we're performing an addition reaction, and we're going to an alcohol, which is unsaturated. Okay. Remember that the functional group for an alcohol is OH. Oopsie, the hydroxyl group. Okay. Then, I'm so sorry. I'm having the most abysmal internet problems tonight. My router keeps dying. So I hope it's fixed now. Oh, my. Yes, I'm. Okay, let's just start from the top. Work through this whole reaction scheme again from the top. Okay, so alkenes, because they have double bonds, are unsaturated. Okay, you are right, I did get them mixed up. It happens. Okay, alkenes are unsaturated. Okay, they still have carbons that are bonded to carbons with double bonds, so they're unsaturated. Alcohols and haloalkanes and alkanes are all saturated. All right? Carboxylic acids are saturated, and so are esters. Okay, so everything in this reaction scheme is saturated except for your alkenes. Okay. Now, when we go from an alkene to an alcohol, this is going to be an addition reaction, and it's called a hydration type addition reaction. If you're going backwards, it's a dehydration reaction. So you'll see that often a addition reaction, is paired up with an elimination reaction going the other way. So hydration and dehydration, halogenation and dehalogenation, or more commonly dehydrohalogenation. Hydrogenation, dehydrogenation. All of these are paired up. Not all, but most are paired up with a reverse reaction that is the opposite type. Okay. Wonderful. So, here is the thing. All of these reactions only happen under very specific conditions. All right? And you need to know these conditions. So you need to know what the specific type is, moving, for example, between, if I say to you, okay, I'm going from an alkene to a haloalkene, you need to tell me I am halogenating or hydrohalogenating that alkene. If I tell you I'm going from an alcohol to a haloalkane, you need to be able to tell me that that's free radical halogenation. These names of reactions and what type of reaction they are is incredibly easy to memorize because the names tell you what they're doing. If you're hydrating something, you're adding water. If you're hydrogenating something, you're adding hydrogen. If you're halogenating something, you're adding a halogen. If you're esterifying something, you are making an ester. Okay, these names are easy to remember. All right. Check the Q&A. What's in the Q&A? Yes, carboxylic acid, COOH. Correct. Okay, I've answered that one. Cool. So these names are easy to remember, and you can score easy marks. For example, something that they like to do in a paper is they might give you an arrow like this. They give you a picture like this, and they tell you, okay, this is an alkene. They give you that, and this is a haloalkane, and they ask you to label this arrow in the middle, this yellow arrow, for example. That's easy. You're going from an alkene to a haloalkene, so you need to be adding halogens. So halogenation or hydrohalogenation. There will be clues as to which is which one it is, other than just the arrow. Okay, so maybe this was a bad example, but they can give you a picture like this and ask you to label an arrow. Or they can give you, for example, an alkane. They can give you an arrow that says free radical halogenation, and you need to tell them that you're going to get a haloalkane out of that. All right. Major and minor products. Okay. I will try and address major and minor products, but I feel like that's maybe a bit advanced. So let's see how the session goes with dealing with reactions first. And then if everyone is okay with that, we will come back to major and minor products because that is quite advanced. All right. It is in the scope of your syllabus, but I am sticking to questions that are a bit simpler to approach. All right. So, with this picture in mind, and I suggest if you are someone who likes having a picture to study from, feel free to screenshot this. Feel free to copy it down. Like, please take your own notes, copy it down, screenshot it. I'll give you a couple seconds to do that, and then we will move on to the conditions under which these happen. Okay. Take your screenshots. Oh, lots of questions in the Q&A. Okay. Esters cannot move back normally. You don't need to worry about moving an ester back. Okay. Are alkenes saturated? No, alkenes are unsaturated. What about the reaction conditions? We're going to get there. Esters moving backwards, you don't need to worry about. Okay. That answers all of those, I believe. Yeah, we're going to get to the reaction conditions now. All right. I hope everyone's taken their screenshots because I'm going to move on. Okay. I'm going to start with the different substitution reactions. Substitution types. Right. So, the substitution types that you need to worry about are free radical halogenations. Okay? Now, depending on where you're coming from and whether you're adding a halogen to an alkane or to an alcohol, the conditions change. Okay? So they are both called free radical halogenation, confusingly, but the conditions are different depending on where you're coming from. So if you're coming from an alkane, just get a pointer. If you're coming from an alkane here, you're going to break your halogen with UV or with heat. Okay? Either or. And you're going to get to a haloalkane. You can do the same thing coming from an alcohol, but you have to treat it a little bit differently. Alcohols also tend only to accept bromine or iodine, so the heavier halogens. I'm not going to go into the mechanics of why, just know that that is the case. Alcohols tend to accept the heavier halogens. And to do this, you're going to heat it under reflux. Um, Heating under reflux is a bit of a weird term if you've never been in the lab. Yeah, UV stands for ultraviolet. Ultraviolet electromagnetic radiation. Okay. UV stands for, excuse again my terrible handwriting. Ultraviolet light. Okay. The sun gives off ultraviolet light. Part of it also gives off white light, which is why we can see. But the sun does give off UV. That's the most common occurrence of UV that I can think of. It's why we wear sunblock when we go outside, or a hat. All right. So yes, UV stands for ultraviolet. And this is not sun levels of UV. This is not going outside on a sunny day levels of ultraviolet radiation that you're exposing this to. This is extremely high levels of ultraviolet radiation. This will burn you very badly. Okay? Then, if you're going from an alcohol using the bromine or adding bromine or iodine, you're going to heat under reflux. Now, if you've never been in the lab, which I understand a lot of you maybe haven't, heating under reflux means that you have your little vessel that has the reactants in it. So your reaction is happening in here. Okay. And you're heating this, so there's a little flame. Okay, pretend I can draw, please. There's a little flame. And you're not letting any of the steam from this escape. So all that it means to heat under reflux is you're not letting the steam escape. So there's a cork in your vessel. Okay, some labs may have a much more involved setup than this, with special fancy equipment for the purpose. But all that it means to heat under reflux is that you're not letting any of the steam escape. Yes, it is. Heating under reflux is in your exam guidelines, but they don't expect you to know what it means. I'm just telling you because when people told me heat under reflux, I didn't know what it meant. Okay? Heating under reflux means heating without exposing the steam, letting it go off into the atmosphere. Okay. Then let's move along. So they're not going to ask you, for example, to draw a setup for heating under reflux. Okay? They're not going to ask you to draw the setup. It's just, you have to know it's heating under reflux. All right. So, moving on. Oopsie daisy. Hydrolysis. All right. Hydrolysis means this word. Hydro is water. And lysis means breaking. Okay. So if you draw a haloalkane, example, let me draw that on the reagent side. Sorry. If I draw a haloalkane, I've got some halogen, and I have a bunch of hydrogens. Okay, all the rest is hydrogen. I'm not going to write out 100 H's. All the rest is hydrogen. Then what happens here is that I am changing out this halogen. I'm breaking it off. So that's the breaking part. And I'm changing it out for a hydrogen atom. Okay, because water, remember, you can break this down into being a hydrogen atom, H+, and OH minus. Okay. Now, OH minus is the functional group of your alcohol. So you are going to add this OH group on to make an alcohol. But you first need to break off the halogen that's in the way. So that's why it's called hydrolysis. Okay? And for all of this, you are again going to heat this under reflux, but you're doing that in the presence of a very strong base. No, heating under reflux does not change your chain length. None of these will change your chain length, except cracking, which we'll get to. Okay, can I please repeat? Yes, sure. Hydrolysis. Okay. You all know that hydro, the word hydro, means water. That's why we say, oh, did you hydrate today? Did you drink water? Hydro means water. Okay? So this is H2O, water. And water can break up into H plus. Water can break up into some interesting configurations, but for the one that we're interested in, breaks up into H plus and OH minus. Okay, now you can see here an alcohol's functional group is OH attached to a carbon. So for example, if you had a carbon here, a carbon there, and a carbon there, and you have more carbon chain going that way, this is an alcohol. Okay? So this OH from the water is what's going to turn your haloalkane into your alcohol. Now, lysis means to break. Okay, this is breaking. Sorry again about my handwriting, and it keeps getting worse. Okay, but you're breaking. So, what are we breaking? We are breaking the halo off the haloalkane. We are breaking off the halogen. And to do this, to turn a haloalkane into an alcohol, it's not magic. There's fantastic chemistry behind this. You are going to add a strong base, so sodium hydroxide, this one, or potassium hydroxide. Oopsie. And you're going to heat it all under reflux so that nothing is escaping, and then it will give you an alcohol. And this alcohol that you are getting is coming from water. Okay, so the strong base that you are adding is not consumed in the reaction. The strong base is a catalyst. Catalysts, you'll do this when you do rates of reactions, if you haven't done them already. A catalyst is something that speeds up a reaction without being used up by that reaction. So the strong base in this situation, along with the energy from the heat, are catalysts to turn haloalkanes by hydrolysis into alcohols. Are you happy with that set of reaction conditions? Yay! Okay, seeing thumbs up, that's good. Okay, so guys, this is stuff you can memorize. If you spend a couple of hours somewhere in your life and you sit with this, you will be able to memorize it. It's not very difficult. Okay? You can spend a couple of minutes, listen to some music, and just learn them, and it'll stand you in good stead. Okay, you will be able to get marks just by learning the reactions and learning their conditions. Moving swiftly along to hydrogenation. Now, this is interesting, and the mechanics of this, if you are someone who likes to do some research, it's very interesting. Hydrogenation does what it says on the tin. It adds a hydrogen. or 2 hydrogens, normally. Okay. You can see here that we're going from an alkene on this side, alkene, to an alkane, which means that let's use ethene again as an example because it's nice and easy. Let's say we have just stock standard ethene. Okay, that's my ethene. When we're doing hydrogenation reactions, what is happening is that we are taking this little bond in the middle here, one of them, either one, it doesn't matter, and we're going to open it up, okay? So, like if you have one of those tables that the legs fold in, it works kind of the same way. These legs are just folded in, they're making that double bond, but we can open them back out, all right? So what we're going to do is we're going to break this bond open, and we're going to have C single bonded C. Okay. But for this to happen, we need to stick something on here to make these carbons happy. We can't just have bonds floating off and not bonding to anything. So we already had hydrogens, 2 hydrogens per carbon that were here already from the beginning. They've always been here. And all that we do when we do hydrogenation is we open up that bond that I've circled in blue and we stick on to the ends of that bond 2 new hydrogens. That's it. Okay. Please check the Q&A. Sorry. Yeah. So will water take out the halogen into alcohol? Okay. I'm gonna go back to my previous slide so I can just show you what's happening. Okay. Okay, so people have asked me to just go back to hydrolysis quickly. So, will water kick off the halogen and add the OH for the alcohol? Yes. You use the water to kick off the hydrogen. And then the OH from the water is what's going to form the OH for the alcohol. So yes, that is correct. Can I explain hydrolysis again? Hydrolysis I have shown twice, but I will show again. Hydrolysis, when water is split up, hydro, H2O, looks like this. Remember, that's what your water molecule looks like. This can break up into H plus, thank you, and OH, OH minus, and remember, OH minus. Remember that OH minus is the functional group for an alcohol. That's the most important part that you need to know, is that water is contributing the OH minus that you're going to need to form your alcohol. The heating under reflux bit and the using the strong base as a catalyst bit, you just need to memorize. Okay. Yes. Alrighty. Then I'm going to go back to explaining hydrogenation, which is what we were busy with. Okay. So, in hydrogenation, we're doing this opening like table, like a trestle table, and we're adding on these new hydrogens. Do you agree with me that the molecule that I've drawn at the bottom, this, is not ethene, but it's ethane. It's an alkane now. Ethane. So we've gone from being an alkene, ethene, to being ethane, the alkane. All right, good. Where can we find these notes? They will be uploaded to the Learning Space social media. Okay, so go check out the YouTube, and there's TikTok, and there's whatever platform you prefer. There will be some version of both the lecture, and I will also send a PDF of the notes that you can use. Um, so that is hydrogenation. Now, I told you that almost all the addition reactions are coupled to an elimination reaction, or have a sort of opposite elimination reaction. And for hydrogenation, that's dehydrogenation. Okay. Now, this is exactly the opposite. What we're doing is we are taking ethane, so carbons, each with 3 hydrogens. I'm so sorry about hydrogens, and we're going back to being a carbon double bond with 2 hydrogens. So the above one, we were going from ethene to ethane. Now we're going backwards from being ethane to ethene. Where can we find the PDF notes? They're not currently available. They will be made available afterwards. You should be taking your own notes. Okay. Now, to do this, we are going to need some heat. Heat is a common trend in most of these reactions. Not all, but most have heat as a requirement, okay? And this one has a catalyst as well. It's chromium oxide, Cr2O3. I'm not going to go into the mechanics of how chromium oxide moves this reaction, but it's a catalyst. So these are the two conditions. To go from an alkane to an alkene by closing up the legs of the table, as it were, you are going to use chromium oxide and you're going to heat this. Okay. Are we happy with that? So we're happy with forward, ethene to ethane, and we're happy with backwards, ethane to ethene. Yep, okay, good. Check the chat, check the Q&A, didn't see anything. Wonderful. Good, 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 good. Okay, so let's move on to the next portion. Halogenation. Now this is fun, okay? Halogenation, you see there I've put that it is spontaneous. A spontaneous reaction means that without me doing anything, without me as the scientist telling this molecule, hey, could you please do what I want you to do? It just does it. I put everything in a bottle and it does the thing. Halogenation is like that. It's wonderful, okay? If I'm halogenating something in the lab, I put an alkene in there, I put some halogen in there, and I get a haloalkane without having to do anything. It's fantastic, okay? Halogenation, there are no conditions. It's spontaneous. If they ask you, they will not ask you for conditions for halogenation because there are none. Okay. So if they ask you, is halogenation spontaneous? Yes, it is. Yes, all of these need a non-polar solvent, okay? Some of these you can do in water, but all of these need some kind of solvent. A non-polar solvent here is preferred because it's not going to compete with your halogens. But you don't have to heat this. You don't have to add a catalyst. It'll just do what it needs to do. Okay. But then, like I told you, for every addition reaction, there is an elimination reaction. And the elimination, oh, sorry, we need to do hydrohalogenation first, which is different. So, hydrogenation versus hydrohalogenation. What does the nonpolar solvent do? Okay, gonna answer you live. And any solvent is just making an environment for a reaction to happen in. All right. And the non-polar solvent just means that it's not going to compete with the extremely polar halogens. Okay, because if you had a polar solvent and you have polar halogens, they're going to compete with each other. They're too similar. They're going to compete for the same reaction. So that's why you want a non-polar solvent for halogenation. Any solvent, be it polar or non-polar, water is polar, is going to just create an environment around the molecules that are actually participating in the reaction. But sometimes you can induce or start competition between the solvent and the molecules that you are interested in. For example, if I tried to do this reaction in water, the negative OH group in water would compete with my negatively charged halogens. Okay, which I don't want. So I use a non-polar solvent. Like, for example, ethanol is a good non-polar solvent. It's another organic molecule, but that doesn't matter. I can use it as my non-polar solvent. And it will not compete with my halogens. Okay. Check the chat. Great. Happiness. Let's move on. Hydrohalogenation, which is very, very similar, but not exactly the same. Here, you are taking an alkene. You are adding an acid to it. A hydrogen bonded to a halogen is pretty much always an acid. Some are strong acids. Hydrochloric acid and hydrobromic acid are strong acids, and hydrofluoric acid and hydroiodic acid are weaker acids. Doesn't matter, they're all acids. So you have an alkene and you add an acid. And that will give you a haloalkane, but it is very, very important that you keep this dry. You do not bring water anywhere near this. Why? For the same reason that you use a nonpolar solvent for halogenation. Water will outcompete your acids. Okay, you want these acids to stick on to this alkene. Okay, let me give you an example of what this looks like. Say, again, let's take our good old friend. You guys are going to see lots and lots of ethene today. Okay, say you have ethene. Good old friend. Okay, and now I bring close to ethene in the absence of water. HF matter. The electrons that are in this double bond, remember there's two electrons here. So there's one electron there and one electron there. The electrons that are in this double bond are going to pull this double bond open and form a bond with H and a bond with F. And you're going to end up with this. Hydrogen and a hydrogen and a hydrogen. Guys, aren't you glad I'm not drawing octene? I would be here forever. And a new hydrogen that's coming from your acid, and a fluorine that came from your acid, a fluoride, I should say. Okay, so this is what's happening in hydrohalogenation. And this happens in the absence of water. So this can be in a non-polar solvent, or it can just happen dry, which is to say there's no water added, you just put these two things in a vessel. Okay. Let me see quickly. I'm hearing that I have network issues. Let me see if I can sort that out quickly. Hopefully my network is a bit more stable now. Did everyone catch what I was saying about moving from ethene to fluoroethane? Yes. No, yes. Okay. See, there's questions in the Q&A. Yeah. Okay, I have checked my network. Let me know if my network is still being an issue. Yeah. Anhydrous means there is no water added. That's correct. You're not adding water, but there should also be no water whatsoever. So you're not working with water as the solvent. You're going to have all of this stuff dissolved in, for example, ethanol, or some other non-polar solvent. And yeah, just ticking off your correction as being answered as well. Cool. Please re-explain. Sure. Okay. Let me draw. So here I have HF, which is an acid, and inside the double bond here, I have two electrons, because that's how bonds are formed, where you have two electrons that are like reaching out and touching each other. More or less. Electrons don't actually touch, but you can think of it as that. And what happens is when an acid comes close to this type of double bond, these two electrons look over and they say, oh, we want to stick onto this acid molecule. That's going to be super, super cool. So they run off and they go and they form new bonds. They form the bond with the H, and they form this bond here, there, with the F, the fluoride. All right. And that's how we've gone from ethene with this double bond to fluoroethane with a single bond. Oh my goodness, and I've clicked through like half my slideshow. There we go. Is that a bit clearer? Better. Okay, good. Let's move on. Okay, I do at this point foresee the lecture going slightly over time. So if you can stick around, we're gonna do one more question at the end. Okay. Dehydrohalogenation. This is the opposite. All right. And this happens again, we're using a strong base as a catalyst. Hello again, old friends. Sodium hydroxide and potassium hydroxide. This all again has to happen in anhydrous conditions. So no water, and we're going to apply some heat. In this situation, we are moving from being a haloalkane back to being an alkene. Okay, you might also, in American textbooks, see halogenoalkanes, or them being named as halogenoalkanes, it's the same thing. Sorry, let me just look what's happening in the chat. Ene. Where will the hydrogen go and where will the halogen go? Okay. So anonymous person who asked about pent-2-ene. This has to do with your major and your minor products, but your hydrogen will favor the more heavily substituted carbon. So your hydrogen wants to hang out with other hydrogens, and the halogen will go on the other side. Okay. I hope that answers your question because I don't want to get into major and minor products here. We don't honestly have time, and I would like to cover the basics. But if that answers your question, I'm happy. But for those of you who have no idea what I'm talking about, major and minor products, don't worry about it. You can do most of these questions without knowing major and minor product. So focus on getting the reaction schemes down, the reaction conditions and the types and the products and the reactants. Yeah. Okay. Thank you. The person who's saying thank you, and thank you very much. I'm glad it's helping. All right. Okay, we're not quite done yet. We have a couple minutes to go, and I'm going to try and finish the slideshow before we all get absolutely exhausted. Okay, dehydrohalogenation. It's the same anhydrous conditions. Whenever we're working with a halogen, it has to be anhydrous because water outcompetes a halogen. Okay, it's like having Usain Bolt and someone who's lazy and never gotten off the couch in their life in the same race. Water is Usain Bolt. Water will win. Water will outcompete. So, anhydrous conditions, okay, for halogens. Anything to do with halogens. Hydrohalogenation, halogenation, dehydrohalogenation. If there's halogens involved, we don't want water. Okay. Then we can move on. If there's nothing in the Q&A and I don't see anything in the chat, I'm going to move on and we can talk about hydration. Now, here we are adding water. Okay. Hydration, we're adding water. And here's the thing. When we, in organic reactions, are working with water, and it's not the solvent, because here it's not the solvent, here we're trying to stick it on. We work with it as steam, okay? Because then it also does the heating up of the reaction at the same time. That's why we do this. So we have the alkene, and we add it to some steam, and the catalyst for this is phosphoric acid. Okay, H3PO4. In this, the H3PO4 being a catalyst, I reiterate, is not consumed by the reaction. The H3PO4 that I put in at the beginning of the day is still there at the end of the day, but my alkene and water have reacted to form an alcohol. Okay. Please repeat, Pomelelo, which part? If you could just specify, I'm going to say I've answered this part, but can you just let me know which part you want me to repeat? Okay. Give you a couple of seconds before I zoom off too fast. Do you want me to repeat dehydrohalogenation? Let me go up. Okay. H3PO4. I'm going to type my answer to this because you need to know how to spell it as well. It's phosphoric acid. Beginning of hydration, sure. Okay, beginning of hydration, I was just saying that we are adding water. So we are adding an H and we are adding an OH. Okay, which, when we're adding it to an alkene, is going to give us an alcohol. which is what I have drawn out here. All right. We're adding the water as steam because we're adding heat at the same time. Steam is very hot, so we are heating and adding water at the same time by using it as steam. All right. Let's see. How's the chat? Okay. Gonna quickly move on so we can get to a question. Dehydration, it's the exact opposite process. We're going from an alcohol, we're taking off an H and we're taking off an OH, and we're going to get back to being an alkene. This also needs heat, and it also needs an acid, but it is a different acid. Okay? It's H2SO4, sulfuric acid. Okay? S stands for sulfur, so it's sulfuric acid. So a way that I used to remember this is H3PO4. Is hydration similar to hydrolysis? Yes, they are quite similar. The only difference is that hydration, we are starting with an alkene. We are starting with something unsaturated in hydration. And hydrolysis, because it's substitution, we're starting with something that is fully saturated already, and we're just swapping it out. So hydration is we are adding water. Hydrolysis, we are swapping water for something else. Usually hydrogen, but it can be a halogen as well. Okay. So I used to remember this, which acid goes where. P for papa, like father. I'm Afrikaans, so I call my dad papa. As in father, right? Your father like picks you up and puts you where you want to be. So you're adding your water, so it's like putting a child, like a dad picking up their kid on their shoulders. Okay, so that's how I used to remember that. And then heat, SO4, I don't know, I just remembered that the acid, the P, was adding water. Okay. So learn the difference. The two acids do behave differently as catalysts. Okay. Then esterification is a special type of dehydration reaction, and I'll show you why. Because when you have an alcohol and a carboxylic acid, so let's draw something. Okay, let's draw methanol, H's. Okay, I'm not going to draw all the H's. Okay, OH. That's methanol. And let's draw ethanoic acid. Okay, so hydrogens. If I don't put anything on the side of the bond, it's a hydrogen, because otherwise I will be here forever drawing hydrogens and we'll never get anywhere. All right. So we have methanol and we have a ethanoic acid. When these two things react, they're going to form an oxygen bridge, which sounds a bit bizarre, but remember what I showed you, they form this structure. Okay, so this part in the middle is called an oxygen bridge. You can also have sulfuric bridges. For example, the organic molecule that makes up your hair has sulfur bridges, but don't worry about it. It's just for your interest. What's going to happen when you bring these two things together and you heat them up with some sulfuric acid is that you're going to snap off this here, and you're going to snap off the H on the alcohol. So always a hydroxyl group from the carboxylic acid and just the H from the alcohol. Is H2SO4 sulfuric acid? Yes, it is. Okay. So you're going to snap off the H and you're going to snap off the OH. And these two are going to run away together and become water. So can you see how this is a type of dehydration reaction? Because you're taking out a water, but it's just not all coming from the same place. Okay. And that's why these conditions are the same as the conditions on the previous slide for dehydration. All right. I hope if that clarifies something for someone, maybe it made some light bulbs go off. So that's how we get to these reaction conditions. And then this is going to be methyl ethanoate, this compound. All right. One last one. We're going to do some cracking. Let's just erase this before we go on. Okay. Cracking. Okay, so cracking can happen under two different sets of conditions. You can have what they call mechanical cracking, which is where you apply heat and pressure. Or you can have catalytic cracking, where you apply the catalyst, whoopsie daisy, where you apply the catalyst zeolite. Re-explain the ester. Okay, yeah, sure. Let me just go up on my slides. Right. So, oh, okay. To form an ester, you are taking an alcohol. So, something, 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 COH. Okay, so the squiggly lines mean something, something, something with carbon. Okay. And on the other side, you have C double bonded to O, OH. So a carboxylic acid and something, something, something. Okay. Here, from your alcohol, you're going to break off the H. This is going to get off. It's going to go away. Right? And the entire hydroxyl group from the acid. So please, it is always the acid gives the OH. The alcohol only has an H. That is important because if they ask you to draw this reaction, you have to know who is who. And this is also important for naming esters. Okay. So, please, 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 please. The alcohol only gives an H. The carboxylic acid gives OH. Okay. And this gives that OH. Now, this H and this OH are not going to stay free floating in solution. They're going to find each other like friends in a club, and they're going to get back together and they're going to form H2O. Okay. And then if I highlight this in green, this carbon chain and this carbon chain are going to come together and they're going to form C O C oopsie daisy double bond O. Okay. Maybe that's a little bit clearer. If it wasn't clear the first time for you, maybe now it's a bit clearer. So the reason that these reaction conditions exactly match the conditions for dehydration is because you are knocking off a water here as well. All right. So let's move on and talk about cracking. Okay, good question. Let's talk about naming esters because this throws people for a loop. let's talk about naming esters. Okay. So let us say that we have the following ester. If I could get to my pen, that would be lovely. Okay, let's say we have this ester. We have C, C, double bond O, O, C. Okay, and please remember that for my own sanity and yours, if there's nothing on the side of a bond, it's hydrogen. Okay? So, here. When we were forming this, do you remember that we broke off an OH group from the carboxylic acid side? So, when you break an OH group off a carboxylic acid, that carboxylic acid becomes an ion that we denote something something O8. O-A-T-E. Okay. Like so. Oh, wait. Maybe that's not a very clear T. Okay. So when we name this then, we look at the alcohol side. We say, okay, well, this is a methyl group. Okay, ignoring the alcohol bit, this is a methyl group. Okay, that's methyl. And on this side, we have eth, ETH. Okay? Now we have ethan, O8. This is ethanoate. Okay, the whole ion all together is called ethanoate. So that's where this name comes from. It's going to be methyl from this side, ethanoate from the other side. See? Hopefully that's clear. Oh, okay. Um, is this a bit clearer in the chat? Yes. Okay. Great. So that's how we go about naming esters. And we are going to get to a question where we're going to name an ester in a minute or two. Okay. When you are cracking something, okay, we do this to make all kinds of things from oil. So from oil, we can crack that down into octane, into butane, into propane. This is taking an enormous hydrocarbon. So these are normally hydrocarbons with 12, 13, 14, 15 carbons in them, and we're going to break it down into something smaller. There are two ways to do that. One, you can go the mechanical route, so you can apply heat and pressure. Okay, so this first bit. Or you can use a catalyst called zeolite, which I've written out for you there. Can I just see what's happening in the Q&A quickly? Methyl from alcohol and the ethanoate from the carboxylic acid. Okay. So methyl from alcohol and ethanoate from the carboxylic acid. Okay, it's not just methylnoate, it's methyl ethanoate. It's two separate words. Okay. So there's two ways to go about this. When you are cracking, okay, if you just get told you're cracking something, it's like dropping a bowl. You don't know if you're going to get big pieces or if you're going to get small pieces, and what is the ratio of pieces going to be? You have no idea. unless they tell you what one of the products is. Okay? So all in all, your carbons have to add up. So for example, if I'm cracking nonane, so that's 9. Okay, if I'm cracking nonane, that's 9 carbons. Right? If I'm cracking nonane, it can split into 1 and 8, can split into meth and oct. It can split into eth and hept. It can split into prop and hex, or it can even split into bute and pent. I don't know which one it's going to split into. Okay? They have to tell you one of them. They have to. And they will be telling you at the same time which one has cracked down into an alkane and which one has cracked down into an alkene. So you always have to have one alkane and one alkene when you're cracking. Okay, so alkane, the saturated one. Oopsie daisy, that's a horrible S. The saturated one, and alkene, the unsaturated one. All right? So for this situation, if I told you that I'm cracking nonane and I get pentane, then you know, okay, so pentane has 5 carbons. Well, I have 4 carbons left. I can't destroy a carbon during cracking. I can never destroy a carbon. Okay, so I know I need to somehow get 4 carbons out of this, and what's left is an alkene. So I have to get some butene out of this. Okay, and you can do this exact same process for 12, 20, 200 carbons. If they tell you one, then you can solve for the other one with a relative amount of ease. Okay, so that's cracking. Let's move on, and it's a question, and then we will close off for the evening. I know I am over time, and my apologies. Okay. So, let me just erase all my scribblings. Right. Compound F, they tell you, is formed when a carboxylic acid reacts with another organic compound, mystery compound X, in the presence of a catalyst. All right. So this is already giving you a clue. You're going from carboxylic acid to something, which is F. Now, what homologous series is F, this compound that they've written out? Ma'am, what is the aim or purpose of cracking? Okay, so the purpose of cracking, for example, when you get oil out of a drill hole in the sea floor, those massive hydrocarbons with 20, 30, 40, 50, 100 carbons are not very useful to us. Because the bigger a hydrocarbon is, the less it wants to react with other stuff. So we want to break those big hydrocarbons down into being smaller and more useful hydrocarbons. For example, propane, we burn, if you buy a bottle of, like a gas bottle, that's propane gas. If you drive a vehicle or you know someone who drives a vehicle, a petrol vehicle, that's octane. So that's why we crack. Cracking is going from something big and inert and doesn't want to react down to smaller stuff that will react, that is useful for us. Okay. In the chat, put your answers. What homologous series is F? Is it a aldehyde? Is it a ketone? Is it a carboxylic acid? Is it an ester? What is F? ketone ester. I'm just reading out the answers. Ester. Okay, I'm seeing one ketone, one ester. Ester. Okay. Seeing more answers for ester coming in. All right, good. So, I've gone and I've drawn it out for you. Here, I can again sort of draw in what I've done. So there's this CH3, there's this carbon, there's one O, there's another O. Then these CH2s are linking pieces. So link and link, there's two of them, and then a terminal CH3. Okay, so that's how I've drawn it out. You're welcome to take a screenshot at this point because I'm unfortunately running out of time, so I'm not going to be able to re-explain this. So take a screenshot and see if you can explain it to yourself. I'll give a few seconds. Okay, hope you've all taken your screenshots. Rightio. And when I've erased all of this functional group that I've highlighted here, it's an ester because you have this oxygen bridge. That's what tells you it's an ester. Okay, another clue that it's an ester, if you go all the way back up to your reaction scheme, the only thing that we do with a carboxylic acid is esterification. The only thing a carboxylic acid ever turns into for your purposes is an ester. So by the fact that they've told you it's coming from a carboxylic acid, that was already a clue that it is an ester. Okay. Happiness. Then I've gone and I've broken it down. The carboxylic acid here is ethanoic acid. There's two carbons in this carboxylic acid. So 2Eth, ethanoic acid. And on the other side, the alcohol is 1, 2, 3, meth, eth, prop, propanol. The alcohol is propanol. Okay. So if we had to name this compound, we just talked about naming esters, how would you name it? Propyl ethanoate. Yes, very good. This would be propyl ethanoate. Good. So now let's answer some questions about propyl ethanoate. Okay. So I've told you also here that this is the alcohol chain, so this mystery organic compound X is an alcohol. Okay. The name and the formula of the catalyst for esterification is what? Answers in the chat, please. You can give the name or the formula or both. We need both at the end, but you can give the name or the formula. Sulfuric acid, yes, very good. You are absolutely right. It's sulfuric acid. We're going to need some heat as well to get this to happen. But the chemical catalyst for this is sulfuric acid. Absolutely right. Okay. The type of reaction, it is an elimination reaction, specifically esterification. The structural formula of F I've already drawn out. And when you get a question like this, I would actually recommend, before you even worry about what the reaction is, always draw out your molecules. When you get given something that looks like this, guys, I didn't know what this was until I drew it out. Draw out the molecules that they give you. Because normally, if that question, like these types of questions will always have somewhere where they give you 2 marks, maybe 3 marks for drawing the molecule. Practice drawing organic molecules. They're not as scary as they look. The number 1 rule is every carbon has to have 4 bonds. If you can make all the carbons have 4 bonds, you have probably done it right. Okay. So practice. Change up. There's a whole table of molecules in this paper. I'll go back to it and show you. Practice drawing them. Draw all of them. Draw all the organic molecules that you can think of. Change them up. Switch them around. Do something interesting with them. Practice. Okay. Then, what is the IUPAC name of the compound X? Okay, we did talk about it. Can anyone give the name in the chat? The IUPAC name for compound X. Propanol. Yes, it is a propanol, but you have to tell me where that hydroxyl group is. Okay, so yes, we have said it's propanol, but is it propan 1-ol, propan 2-ol, propan 393-ol? It's propan 1-ol. Okay. So when you are naming an alcohol, the same way that we spoke about when you're naming an alkene or an alkyne, you have to tell me where that functional group is. All right. So with these groups that the functional group is the homologous series name, before you put the suffix propan 1-ol, for example, or prop 1-ene, or put in the numbers for where the functional groups are. Don't forget. Yes, propan 1-ol. Okay. And that is the end of this question. And that is the end of the slides that I have prepared. I will go back to that table with the organic molecules so that you guys can take screenshots, practice drawing them, practice naming them, think about what reactions can you do on them, think about what the conditions for those reactions would be. It'll be very, very good practice for you because these molecules are all from last year's paper. So they are the types of molecules that you will probably see in your prelim and probably then as well in your final. Okay. So don't be alarmed when I leave the slideshow. Number 3. Okay, number 3 is asking to draw the molecule, which I have already done for you. Okay. The structure is up there with the 2 components circled. Okay. So yeah, question 3 I had already done for you by drawing it out. Okay. Let me leave annotations. Here we go. And go back up to where I had this whole table. There we go. Take a screenshot of this slide and practice with these molecules. It's good practice. Okay, then thank you very much everyone for coming. I hope this has been helpful. I know organic chemistry is a bit tough, but I hope maybe that I've shown you some of the logic and the systems behind it, and hopefully that makes it a bit easier. Okay. Have a good evening, study well, good luck for your prelims, And we hope to see you all again before finals.